This figure shows the upsampling by a factor of 3 of a sinusoidal sequence with a frequency of 0.12 hertz. I think you can understand this. Left figure shows the input sequence x n, and the right hand side figure shows the upsampled version of the input sequence x n with the upsampling factor 3. Then we should discuss downsampler. First we should have a look at the time domain characterization, very important. When we talk about a digital device, we should have a complete picture of that particular digital device, means we should study or analyze the time domain characterization as well as frequency domain characterization. Digital signal processing, both are equally important. First you should have a time domain characterization, then you should go for frequency domain characterization. If you try to do some research in this area, and if you want to produce some research articles, you should provide both time and frequency domain characterization for your filter that you have developed. So, time domain characterization is important. So, you should know the time domain characterization of a downsampler first. A downsampler with a downsampling factor m, where m is a positive integer, develops an output sequence y n with a sampling rate that is 1 divided by mth of that of the input sequence x n. So, reverse is the situation here. Upsampling we have understood. Through upsampling business, I can increase the sampling rate by a factor of L. Here I can decrease the sampling rate. Downsampling means I can decrease the sampling rate by a factor of capital M. So, sampling rate can be decreased by an amount mth of that of the input sequence x n. So, for decreasing the sampling rate, you have to use a downsampler. The block diagram representation has been shown here. X n is the input sequence and capital M is the integer factor or the downsampling factor. This downward arrow shows the downsampling of the input sequence x n. Let y n be the output sequence taken from the downsampler. Downsampling operation is implemented by keeping every mth sample of x n and removing m minus 1 in between samples to generate y n. The simplest method could be to suppress or delete or remove m minus 1 samples in between two consecutive samples, because we are interested here, we are interested to decrease the sampling rate by a factor of capital M. So, how to achieve this? It is very easy. You can simply suppress m minus 1 samples out of given discrete samples. Between two consecutive samples, you have to simply suppress m minus 1 number of samples. So, this way I can reduce the number of samples by a factor of capital M. Thereby, I am decreasing the sampling rate by a factor of 1 divided by m. So, this particular figure shows how to downsample the given sequence x n. Left side figure shows a discrete sinusoidal signal with frequency say 0.042 hertz. The right side sequence is the output from the down sampler. Your downsampler is basically a device. For the time being, we can consider it as a device. So, output is y n. So, this is the output. Here the sampling frequency has been decreased by a factor equal to 3. You can easily obtain this sequence from the given sequence section in the laboratory. By using MATLAB, you can easily generate this sequence, then you apply that particular technique, downsampling technique, means you suppress m minus 1 number of samples in between two consecutive samples, so as to obtain this. So, this way it is very easy to implement a downsampler, but in practice this is not the case. While considering this output sequence, between these two consecutive samples, 3 samples are removed. Here it is not like that. Here you take first sample, then you remove 2 samples, you will get this. Third one should be retained here. The first 2 are suppressed. Then similarly, you suppress this 4th and 5th, then you retain the 6th sample. 6th sample has been retained here. You take one sample, then you suppress m minus 1 number of samples, then you take the next sample. So, between these 2 consecutive samples, 2 samples are already suppressed, thereby reducing the sampling frequency by a factor of m, where m is a positive integer quantity. Then we should discuss some of the basic sampling rate conversion devices. Sampling periods have not been explicitly shown in the block diagram representations of the upsampler and the downsampler. That is why probably I have not explicitly shown the sampling periods. The earlier figures were produced for a demonstration purpose only, how to choose samples from the given sequence section. Those pictures have never shown the sampling period. This is for simplicity only, and the fact that the mathematical theory of multirate systems can be understood without bringing the sampling period capital T or the sampling frequency f t into the picture. Now, I will discuss mathematically how to reduce the given sampling or the input sampling frequency by a factor of capital M, or how to increase the sampling frequency by a factor of capital L. This is for the downsampler device. Downsampler is used to reduce the sampling frequency by a factor of m. Figure below shows, this figure shows explicitly the time dimensions for the downsampler. X n is the input sequence. Basically, X n is a discrete sequence which can be obtained from the analog version, say x a t. T is replaced by n t. You know the discretization procedure. Let x n be the input to the downsampler, then output is y n, which is again a discrete sequence and can be written like this: x a n m t. Input sampling frequency is represented by f t here. This f t represents the input sampling frequency, that is equal to say 1 divided by t. The output sampling frequency can be represented by f t prime, that is equal to f t divided by m, that is equal to say 1 divided by t prime, capital T prime. So, here we can observe that the input sampling frequency is reduced by a factor capital M, where M is an integer quantity. Similar is the case with the upsampler. This particular figure shows an upsampler. This figure shows explicitly the time dimensions for the upsampler. X n is the input sequence, which is again obtained by sampling x a n t, n t is replaced for t, where x a t is the time continuous function and x a n t becomes the discretized version of the time continuous function x a t. Let x n be the input to the upsampler. The upsampling factor is capital L here. Let y n be the output sequence. So, this output sequence can be explicitly written by using the time dimensions as this x a n t divided by L, where n is equal to 0 plus minus L plus minus 2 L, 0 otherwise. Here again let f t be the input sampling frequency, that is equal to 1 divided by t, and f t prime is equal to L f t. Here the sampling frequency has been increased by a factor of L. Again it can be written like this 1 divided by t prime. 0 plus minus L plus minus 2 L, k means again it can be repeated, k is an integer again. This 2 L, 3 L, 4 L, they are all integers. N is an index only. So, you have to choose an origin. If it is a causal sequence, it is always plus only, you need not bother about minus. Usually we deal with causal systems as causal sequences. This is the generalized version of the talk. In practice, always we like to use causal sequences and causal systems. So, this minus n business does not arise in practice, but in some cases when your reference is somewhere other than 0, then the left hand side sequence index is known as the minus n or minus L or minus k. Otherwise, the right hand side values refer the positive index, the plus index. Therefore, by using an upsampler, we can increase the sampling frequency by a factor of capital L. The upsampler and the downsampler are linear, but time varying discrete time systems. This is very useful or important point. When we talk about the multirate digital signal processing, we should understand the features of upsampler and downsampler. Basically, they are linear devices. Linear, I mean they satisfy both the principle of superposition as well as the principle of homogeneity. When both the principle of superposition and principle of homogeneity are satisfied, then we call it as the linear device, otherwise non-linear devices. So, our samplers, both upsamplers and downsamplers, are basically linear devices, but time varying discrete time systems or devices. They are linear, but they are not time invariant, they are rather time varying discrete time systems. I will explain why they are time varying, because here we are using these devices for sampling rate conversion. Therefore, they are time varying. Mathematically also I can justify how these filters are linear, but time varying filters or time varying digital systems. We illustrate the time varying property of a downsampler. The time varying property of an upsampler can be proved in a similar manner. First, we should illustrate the time varying property of a downsampler. Let us consider a factor of m for downsampling. M is an integer factor defined by, say, y n is equal to, y n is the output sequence taken from the downsampler, that is equal to x n capital M. Its output y 1 n for an input x 1 n is equal to x n minus n 0 is then given by y 1 n is equal to x 1 m n is equal to x m n minus n 0. Let us consider a downsampler for downsampling with a factor of m. So, simply y n is x n m, its output y 1 n for an input x 1 n. So, instead of x n, when x n is the input, output is this. Instead of x n, let me give another input, say x 1 n, that is equal to x n minus n 0. What do you mean by this n minus n 0? It is a delayed version of the original sequence section. See, it is simply delayed by n 0 samples, where n 0 is another integer only. It can be 1, 2, 3 like that. So, basically this x n minus n 0 is a delayed version of the input sequence x n. Then the output, when x 1 n is the input, y 1 n is the corresponding output. So, what should be y 1 n? It is simply x 1 m n, that gives you x m n minus n 0, it should be the output, because you know the shifting theorem. Then from the input output relation of the downsampler, we get this y n minus n 0 should be equal to x m into n minus n 0, that is equal to x m n minus m n 0, that is not equal to y 1 n. Therefore, we can claim that our downsampler is a linear device, but it is not time invariant, rather it is a time varying digital system, but it is a linear system, because we are using linear system theory only to design different digital FIR filters, right. Then by using digital FIR filters, we are able to implement low pass filters. Basically, low pass filters are used for downsampling and upsampling of discrete signals. So, this part is clear. Mathematically, we can prove that both the systems, I mean the downsampler and the upsampler, are linear systems, but they are time varying systems. Then we should have frequency domain characterization. As I told earlier, that both time domain and frequency domain characterization is equally important for analyzing discrete time systems and signals. Whenever you read a topic, you should give more emphasis to both time and frequency domain characterization, then you will be able to understand what exactly we are doing in digital signal processing. Consider first a factor of 2. Let us forget about the integer factor capital M or capital L. Now, let it be 2. Let us assume that both M and L values are 2. So, So, here upsampler means I have assumed L to be 2. Consider first a factor of 2 upsampler whose input output relation in the time domain is given by x u n is equal to x n divided by 2. Earlier I have written n divided by capital L. Now, you replace that capital L by a factor 2. So, in time domain the explicit relation for the output sequence x u n can be represented like this. In terms of the Z transform, the input output relation is then given by x u z. I hope you understand Z transform. What is the beauty of this Z transform? Why should we read Z transform at all? Why not Laplace transform or discrete Fourier transform? Basically, your discrete Z transform is a more generalized version of your discrete Fourier transform. As Laplace transform is the generalized version of the Fourier transform. In a similar sense, your Z transform is a more generalization to the discrete Fourier transform. Your discrete Fourier transform is not applicable to all types of signals, whereas Z transform can be applied to analyze different types of discrete time signals and systems. We have more flexibility in discrete Z transform, and you should know what is the link between the Z transform and the discrete Fourier transform. There is a close connection between both discrete transforms. You should know the connection. I understand Z transform to be a more generalized version of your discrete Fourier transform. Therefore, it is very useful for analyzing discrete time signals and systems. You should read more about the discrete Z transform, its properties, they are very important. Then inverse how to compute inverse Z transform, and you should know how to evaluate discrete Z transform of the given sequence. So, here x u z represents the Z transform of the sequence x u n, the transform of the output sequence can be represented like this, n minus infinity to infinity, the generalized version again. If you consider a fully right sided sequence, then the definition is different. This is for generalized signals, means both sided sequences. Say minus infinity to plus infinity x u n z to power minus n. From the basic definition itself, I can write x u z is equal to n minus infinity to plus infinity x u n z to power minus n, that is equal to, for even n, x n divided by 2 z to power minus n, that is equal to say x m z to power minus 2 m, that is equal to x z to power 2. So, it is very easy to get the transform of the upsampled version of the input sequence x n. What is x z? What is x z? X z is the transform of the input sequence x n. So, if I write x z to power 2, then it becomes the Z transform of the output sequence, that is your x u n. Output from the upsampler is x u n. So, this is the relation, very easy to understand. So, accordingly you have to design a filter. So, the input sequence is x n, then the Z transform of the input sequence x n is simply x z. If I write x z to power 2, then it becomes the Z transform of the output sequence, I mean the output from the upsampler, that is x u n. Yeah, here the factor is 2. Similarly, we can consider the upsampler. In a similar manner, we can show that for a factor of L upsampler, x u z is equal to x z to power L, where capital L is an integer again. On the unit circle, for z is equal to e to power j omega, the input output relation is given by x u e to power j omega is equal to x e to power j omega L. Z can be replaced by e to power j omega. This is already known, nothing new in this. We are going to have a discussion for the frequency domain characterization of upsampler. That is why I have replaced z by e to power j omega. This part is clear. So, here I can give you a pictorial representation of the frequency response. This figure shows the relation between x e j omega. What is x e j omega? Frequency response of the discrete sequence x n. In analog domain, normally we use x omega. In discrete arithmetic or in discrete signals theory, we should use x e to power j omega. This is the standard notation which should be used to represent the frequency response of the discrete sequence x n. Similarly, x u e j omega represents the frequency response of the discrete sequence y n, that is the output from the upsampler. Now, for L is equal to 2, in the case of a typical sequence x n, we can study both the figures. From these figures, we can conclude something. This figure shows the frequency response x e j omega means the frequency response of the sequence x n. This figure shows the frequency response of the output sequence, that is y n. Remember that explicitly L is equal to 2 and the upsampling factor is 2, then only we get this particular frequency response. So, here you can observe, here it is pi 2 pi, here we are using the same scale omega versus x u e j omega 0 to pi, here we have pi by 2. So, what happens when you go for the upsampling? When you go for upsampling the input sequence by a factor of 2, what happens to the frequency response? It is more compressed. The folding factor is 2, which you can easily observe from this figure, and these are otherwise known as the images of the frequency response. And when I try to upsample the given sequence by a factor of 2, then the frequency response is compressed by a factor of 2. This much we should remember for all the times to come. In that case, there should not be any confusion. You can easily plot the frequency response of the output from the sampler. It can be seen that a factor of 2 sampling rate expansion leads to a compression of x e j omega by a factor of 2 and a two-fold repetition in the baseband 0 to 2 pi. The original baseband signal, I mean the original signal is assumed to have a frequency response. It can be seen that a factor of 2 sampling rate expansion leads to a compression of x e j omega by a factor of 2 and a two-fold repetition in the baseband 0 to 2 pi. The original baseband signal, I mean the original signal is assumed to have a frequency response like this, which is assumed to be twice pi periodic. It is twice pi periodic in nature. Therefore, the frequency response band is 0 to 2 pi and a factor of 2 sampling rate expansion leads to a compression of x e j omega, that is the frequency response of the input sequence by a factor of 2, as we have seen earlier. Here the frequency response is compressed by a factor of 2, therefore, it is a two-fold frequency response. This process is called imaging, as we get an additional image of the input spectrum. This is very interesting point which should be noted. This particular process is called imaging. This particular word imaging is otherwise also used in image processing literature, but things are completely different. In image processing literature, the meaning of this word imaging is different. In DSP literature, it is different. In DSP, the word imaging is used to explain this particular phenomena. This process is called imaging, as we get an additional image of the input spectrum. As we have seen, we get an additional image when you go for an expansion of the sampling frequency. Similarly, in the case of a factor of L sampling rate expansion, there will be L minus 1 additional images of the input spectrum in the baseband. Low pass filtering of XUN, that is the output sequence, output from the upsampler, removes the L minus 1 images and in effect fills in the zero valued samples in XUN with interpolated sample values. In order to remove those images, we have to use low pass filters. Through this process, I mean through low pass filtering process, we can remove these images and in effect we can fill in the zero valued samples in XUN with interpolated sample values. Zero valued samples are replaced by appropriate interpolated desired samples. Frequency domain properties of the upsampler shown below for L is equal to 4. The frequency domain properties can be studied from these figures. The left hand side figure reflects the input spectrum, omega divided by pi means it is the frequency, and the other scale is magnitude versus frequency, and this figure shows the output spectrum output spectrum I mean the frequency spectrum of the output from the upsampler with L is equal to 4. Thank you all.